Now, if we want to deal with Laplace transforms of complex numbers, if you look at equation 8, and this equation needs to be memorized, the inverse Laplace of capital A constant over s plus little a constant is a e to the minus at. You really need to remember that one. That one you have to remember. And it works for complex numbers also. So the interesting thing is that same formula is going to work for complex numbers, except that if it's a complex number, shown here as p, where p, again, if you remember, p is drawn from the origin of the complex plane up to the pole. And we know that if we ever have the Laplace transform of something with a complex number, we're going to have two of them. And so if you have p, you're going to have a p star that's equal to sigma minus j omega d. And this one, of course, is going to be equal to sigma plus j omega d, or omega n at an angle of theta, where that's the angle theta. So, if that's the case, and this will be the case for a second order system, so the simplest inverse Laplace for a complex is going to be for a second order system. And that's going to give us two poles, one complex p and one complex p star. And if we do the partial fraction PFE, partial fraction expansion of that, then we'll have an arbitrary constant a bar for the first pole and another a bar for its complex conjugate. So we call those capital A P and capital A P star. Now these are called residues. So the numerators have a name, and those names are residues. So there's a residue for the pole P and a residue for the pole P star. And these are evaluated graphically using phasors in a very easy and straightforward. So the next step is to solve for the residues AP. So we want to solve for the residue for pole P, and that's going to be a complex number, and for pole P, AP star, which, as it turns out, this is going to be the complex conjugate of AP. These two guys are going to be complex conjugates. So if we solve for one, we don't need to solve for the other. We just need to take its conjugate. So to solve for AP, this guy, we multiply all the terms by s minus p bar. So if we multiply all the terms by s minus p bar, then we're going to have on the left-hand side, we're going to have a, and this is going to be s minus p star, because we multiplied and canceled. We canceled this one. And then we're going to end up with a p, the residue for pole P, isolated, because when we multiply by s minus p, we'll cancel that term. And finally, we'll have the residue for p star times s minus p, like so, over s minus p star. Now we know that this equation is going to hold for all values of, s of s. So pick s to be equal to p. If you pick s equal to p, then all terms on the right-hand side will be thrown out. They'll become 0, except for what you're looking for. So if we do that, we'll end up with the the residue for pole P that we're looking for equal to the constant A over P minus P star. And we've already seen what P minus P star is. If this is P over here, and this is P star, well then minus P star must go this way, and the sum of those two then is a vertical. So this must be P minus P star. Now this is the important thing to see. If you want the residue for pole P, all you have to do is draw a line from the other pole. Draw a line from the other pole. If you want to have the residue for a particular pole, say P, then you draw a phasor from the other pole. So we see that this is going to be equal to constant A, and we know that P minus P star is going to be equal to 2 omega d times J, or you could put that in the angle form. The residue is going to be equal to A over 2 omega d e to the minus J90. In other words, this is going to be e to the J90 in the denominator, and if I want to move the angle from the denominator to the numerator, then I just have to change its sign. So if this is e to the J90 plus, it'll be e to the minus J90. After we obtain the residue for the pole, we know that the residue for the complex conjugate pole is going to be the complex conjugate of our answer up here. But if you wanted to work it out anyway, and you would see, and of course if you remember, P star was pointing down and minus P, so this would be minus P and this would be P star on the S-plane. So P star minus P would be this vector like so. And now it's going to have an angle of minus 90 degrees, right? So it's going to be minus 2j omega d times j, minus, because it's down, it's minus 90 degrees. And if you brought that to the top, you'd have a plus degree. So we can see that it is, these two are complex conjugates of each other. They're complex conjugates, as we know they must be. And we did need to evaluate what's shown here as equation 13. So now that we have the residues, we can plug them back into the partial fraction expansion. Here's the residue plugged into the first partial fraction expansion. And of course the inverse Laplace is e to the P1t. So there's your first pole, sigma plus j omega d. And the second partial fraction expansion is the second residue times the complex conjugate Laplace transform, which is going to be e to the P star t, sigma minus j omega dt. So if you do some math, do some algebra, you will get this term here, and you will recognize from e to the j theta plus e to the minus j theta over 2 being the cosine. And you can see how we come back from the complex plane into the sinusoid, and it gives us a cosine function. And notice that the angle here for the cosine function is the phase angle of the first residue. In other words, my first residue up here, up at the top in equation 12, the angle of that first residue is minus 90 degrees. And I can see that minus 90 degrees ended up being the phase angle of my sine function. So we only have to do this once, because what we're going to see is that whenever I have a complex pole, that the residue of the complex pole is going to determine the resulting cosine function. And if you look at here, you can see that the cosine function constant that cosine function a over omega d is twice the residue. So you take twice the residue of the pole P and the angle of the pole P, and then you have your cosine function with e to the sigma is the real part of the root and how it decays, and omega d is the oscillation frequency on omega dt for the cosine function. So this completes the second part of complex numbers, and if you still would like some more, then take a look at the